Now that we've went through some of the more in-depth parts of hypothesis testing, let's revisit that McDonald's ice cream cone hypothesis. We want to rewrite our hypotheses below. So as a reminder, our null hypothesis was that mu is 3.2 ounces, what we've been told that the mean for the population is supposed to be, but our alternative, our claim that we're trying to show is true instead, is that mu is not 3.2. We're trying to find evidence that the mean weight of the ice cream cones at McDonald's is not really 3.2 ounces. Okay, let's see. It says, suppose we want to run a hypothesis test with alpha equals 0.05, the standard alpha value. Explain what that means and draw the related normal curve to show the rejection region. Okay, so first I'm going to draw the normal curve, just because that is an easy part here. So what we're going to have is we're going to have some critical value here and here, because this is a two-tailed test, remember? So our related normal curve is going to have a critical value that's positive and also one that's negative. There will be shaded area on both tails, each of these with a value, an area of, remember it's alpha over 2, so in this case alpha over 2 equals 0.05 over 2 equals 0.025. So each one of these regions will have an area of 0.025. And that's what we know that our related normal curve looks like. What does it mean as far as having this alpha value of 0.05? Well, what that tells us is that there is a 5%, or 0.05, a 5% probability of making a mistake and concluding that the mean weight of all ice cream cones is not 3.2 ounces when really it is 3.2 ounces. Because that is how the alpha value is defined. The probability of making a mistake and rejecting the null, so rejecting the idea that it's 3.2 and in saying, no, it's not. We found evidence that it's not, and being wrong, and the mean weight still really being 3.2 ounces. Now it says, suppose you want to instead run a one-tailed test to see if there is evidence that the mean weight of these ice cream cones is specifically larger than 3.2 ounces. Rewrite your hypotheses, explain what an alpha equals 0.05 means here, and draw the related normal curve to show the rejection region. So now, my null would still look the same. I still have been told this whole time that the mean weight, mu, is 3.2. The only thing that changes is my alternate hypothesis, and the only thing that changes is the symbol. So now I'm trying to provide evidence or show specifically that the mean weight is larger. I've now put a direction on it. Image-wise now, I will only have one critical value in the upper direction. I will have one rejection region whose area is equal to the entire alpha value of 0.05. What we've got now is fairly much the same explanation as above. I would still say there is a 5% probability of making a mistake, and concluding that the mean weight of all ice cream cones is more than 3.2 ounces when really it is 3.2 ounces. So notice that the only difference in our explanations of what that alpha value means has to do with the symbol in the alternate hypothesis. So in a difference of saying is not to saying more than or less than. The rest of it is the same. Okay, suppose in our Mcdonald's original two-tailed test that we get critical values of 6.2 and negative 6.2, and the test statistic comes out as a 9.17. Draw this normal curve and decide whether we should reject the null in this case or not. Okay, so let's see what this visually then looks like. So we've got our test statistics, it said, of negative 6.2 and positive 6.2, because it was a two-tailed test. They will always be the same value, positive and negative, of each other in a two-tailed test. So here we've got our rejection regions, here and here. Now what it says is that the test statistic comes out as 9.17. So our test statistic falls way out here at 9.17. So what has happened is the test statistic fell into the rejection region. The test statistic was very far away from the center, very far away from what we expect. We know that the farther away you get from the center of a normal curve, the more unique and unusual and surprising it is. So if it falls into that rejection region, what we're saying is that outcome is surprising enough to tell us we should reject the null. So what I'm going to say here then as some notes is I'm going to say this is far out from the center. It's surprising, unusual of a result to have gotten. So what this is telling us is that since the test statistic falls in the rejection region, we have enough evidence to reject the null. Remember, you need evidence to reject the null. So we could say, now, the mean weight is not 3.2 ounces, right? Because the null was that it is 3.2 ounces. So we found enough evidence to reject that idea, and the alternate claim was that it was not 3.2 ounces. So we have found that evidence in this case. Then it says, suppose that the Mcdonald's one-tailed test, or in that test, we get a critical value of 5.2 and a test statistic of 5.8. This is supposed to be 6.2. Rewrite this, 6.2. Rewrite that. I wanted to use the same test statistic. I'm not sure why that got changed. Let's draw this normal curve. So here's my center. I still get the 6.2 only positive though in this case because it was a one-tailed test. So I only have one rejection region over here. And it says the test statistic that we got is 5.8. So 5.8 would be back here. So what we have here is a test statistic that's not that far out from the center. So it's not so surprising or unusual. So when your test statistic does not fall in the rejection region, What that means is there is not evidence to reject the null. So we do not have enough evidence to reject. So we say we fail to reject the null. So in that case, we have to stick to the original idea that the mean value really is 3.2. It says, notice these above critical values and test statistics were totally made up for this example. So this was not a real test. I just made these up for example's sake. Just to practice when you reject the null and when you don't. And we will soon see how to come up with the real critical values and the test statistics for these types of hypothesis tests. And a note on wording, this is really important. When we fail to reject, it does not mean that you have proved the null to be true. We have just failed in our attempt to show it not true. Maybe if we did more research with more or better or bigger samples, then we might find the evidence to reject the null, maybe not. So you just have to watch your wording. So the phrases that are acceptable, what you would want to say in your write-ups, in your answers, are we either reject that null when we find evidence, or we fail to reject it when we don't. Avoid the words proved or disproved. Proved and disproved are just stronger words that we want to avoid. This means there is a lot of evidence to support these conclusions that we're saying. We have a lot of evidence. We're very confident in them, but it's not 100% foolproof. So we just avoid those couple phrases.